Welcome everyone. My name is Ahmed. I'm an engineering manager in Facebook. For you who have been here in the last meetup, you've probably seen me. I just do the introductions. I don't do that much after that. So I support the zookeeper team in Facebook in general. Today, we have a pretty exciting agenda. I'm very excited. Let's see if my clicker works. We're going to talk about the team itself. We're going to talk about Zookeeper at Facebook. I saw there was a couple of questions in the community once we talked about LAD, about the role of Zookeeper in Facebook. Are we still invested in Zookeeper, or are we changing anything in that sense? And I hope to get you out of this meeting knowing how much we're invested in Zookeeper as a company in general. So we already kind of went through that. So generally, the Zookeeper team, or we have our own nickname for the team, is aiming to create a leading distributed infrastructure or distributed coordination infrastructure for Facebook. We also aspire to be the most reliable, scalable, and simple coordination infrastructure for Facebook. This is my awesome team. Again, for you who have seen this exact slide 2 years ago, we were about half this. We're always growing. You can try to find these people in the audience, chat with them. You can give them a hard time, especially Grayson. You can ask him about his story with the diving or whatever he was doing. Yeah. So I mentioned that I'm going to talk about, to reply to the question of the community of, given that we have LAD, or we talked about LAD as a distribution mechanism instead of just using Zookeeper, is Zookeeper still a thing in Facebook? And yes, it is still a big thing in Facebook. It's still mainly widely used at Facebook for many, many use cases. The only difference that we're in our thinking and philosophy about Zookeeper is, instead of just taking Zookeeper as is and using it in all the possible ways, as a key value store, as a distribution mechanism, as whatever you can mention, how about we build an ecosystem around it and build real systems for each of the things that we consider abuses or misuses of Zookeeper. Some of these will plug into Zookeeper, others are not, but it's still a big use case. It's still, we have a huge and still a big read-heavy use cases in Facebook. It's still used for leader election and locks, metadata, configuration, service discovery. And today, one of the biggest things we want to talk about is, I think this is a big thing for the whole community, is Facebook has been running on Zookeeper 3.6 trunk in production for about a year now. We're going to hear a lot about that, about the journey, and what changes are in 3.6, and also how did we get there, what kind of challenges we've seen. So I hope this is going to be an exciting time for all of us. So I'm going to hand to Fanmin, who's going to tell you about the journey. This is a nice clicker.
Hello. So my name is Fangmin. I joined Zeus team 2 years ago. And I'm going to talk about the Zookeeper journey at Facebook. So we have meetup in 2016. And at that time, we mentioned Zookeeper in Facebook are primarily running in internal forked version from 3.4, and we diverged since then. And also, we set a goal. We want to go back to the trunk. We want to minimize the patch set we maintain internally, and we want to involve more with the community. So what about today? Did we achieve any of these goals? The answer is yes. So we have been, our production example have been running on 3.6 for around 1 year. And we have been upstreaming all our internal patches, and now we have around like 50% of patches being upstream. And also, we involve more with the community. We actively reviewing the patches and GLAs from the community. And I'm happy that I'm a committer now in the community, and we are hoping to have more committers inside Facebook. So yeah, why 3.6? Why chunk? This is a big movement from 3.4 to 3.6. There are a lot of code changes. It's highly risky. And what's motivation? What drove us to move to 3.6? To us, dynamic reconfig is a huge win. It can support adding and removing server dynamically without any loading restart or downtime. So it makes our zookeeper cluster maintenance much easier and safer. Another thing is a new commit processor. It's on 3.6, but not on 3.5, sorry. So it improves the performance of mix, read, write, load, allowed. So here is the example. As we can see, the blue line shows a great improvement in the for read latency. Here, it's around 5x. And of course, we get all the bug fixes from the community for free, which is a huge win to us as well. So we all agree this is the right thing to do. The problem is how we can achieve this without outage with this huge change. Let's see what we did here. First, we need to understand all the patch stats for the last 6 years, which are provided from different engineers. There were around 315 patches at that time. First, we need to categorize and understanding all those patches. For example, patch 1 might be a performance patch. Patch 2 and 3 might be a new feature. Next, we try to minimize the patch stat. So we group them into related patches into one. For example, if patch 3 is a bug fix for patch 2, we merge them into one. Meanwhile, we try to remove unnecessary patches. There are patches which is already in the 3.6 or have a similar implementation. We just remove it from our internal patch. So after we done all these things, we reduce the patch stat from 350 to around 80, which is much less than what we thought of. After this, we are going to implement this on 3.6. There are two ways to do this. We either put the same code, resolve the conflict, do a minor change, and make it working, or we redesign, re-implement the feature, which is what we did for most of our internal features, like new watch manager and read-only observer. So we have all this code ready. So next thing is going to validation, how if there is any new bugs being introduced, if there is any performance regression. This is hard. I think this is even hard for us because we have such a huge change. So what we did here, we created two frameworks. One of them is doing a performance regression detector. Another is doing inconsistency detector. So what does performance regression detector do? It's basically running a bunch of different workload with different type of requests and comparing with the historical data of performance and see if there is any performance regression. Similar to this, we have another framework called inconsistency detector. It's simulating what could happen in reality, like it's killing server, killing leader, and like injecting network fault, and see if there is any consistency issue. And it do help us find one consistency bug in the 3.6. So with all this testing, we have some confidence, and we start rollout. And here are some highlights. We plan small. We plan ahead. This is a huge change with high risk. We need to talk to users and make them comfortable for the upcoming changes. And we categorize those users with different use cases. And we start from small ones, pick those users which is with low risk. After we gain confidence, we expand them to the rest of the world. One interesting might be how long it takes us to fully roll out these to all examples. And here are some numbers. It took 2 months for the 10%, first 10%, and next 4 months to reach to 8%. So last 20% took around 6 months, That's basically because there's examples of most important users. And also with observers, which we skipped at the beginning. And we need to implement those features for observers and doing all this validation testing again. So what we learned, 36 is not perfect, but it's worth the journey, the effort the team put in. There are a few minor issues we found during migration, but those issues are not crazy. After migration, it makes our life much easier. It saves a lot of engineering time. Also, we haven't seen any split brain anymore, which happened before. So performance also improved a lot. We see up to 10x performance improvement on some production examples. And we found new features like TTL is making the garbage collection much easier. So overall, 3.6 is awesome. And with all the bug fixes and new features we upstream to the community, it's even better now. And if you want to understand more about the migration, you can reach out to me during the happy hour. Now I hand over to Joe to talk about the upstream.
All right, hi guys. So yeah, I'm Joe. The slide says I'm going to talk about upstreaming, but that's really only one element I'm going to talk about here. Really what I'm doing is I'm taking off from where Fangman left off. So he talked about how we got from 3.4 to 3.6. I'm going to talk about what are we doing today, how are we developing, how are we upstreaming our features, and what is it that we're upstreaming. So kind of now into the future. So first off, to get things out of the way, we are, as Fangman said, we ported to 3.6 or to master zookeeper. Our plan is to continue to do that. So that's our plan. We're going to keep building off master even when 3.5 comes out, and eventually 3.6. If master is 4.0 in the future, then hey, 4.0 is running at Facebook now. The main reason we're going to do this is two things. First, this allows us to move really fast. We get new bug fixes, new features very quickly. We can react quickly and just get things done. Also, this sort of fits to sort of our organizational culture at Facebook. Generally, this is how we work. We work on master. We write new code. We land new code. We ship new code, and we just keep iterating. If things break, we just fix it forward and go on. So this is sort of our plan to just keep master zookeeper pretty much in a production-ready state, and if it's not production-ready, for us to fix it. I would say as a community, one thing to keep in mind about this is we probably shouldn't commit random experimental features we don't trust, and well, it's master, no one runs that, because we do. In those cases, if we do, we probably want to put those behind a feature flag or things like that so they can at least be turned off. So anything that we don't wholly trust. And if we don't in the community, we'll just add it ourselves. But that's kind of the culture here. Right? Put things that we think we can support and run. The other big reason here is it allows us to prevent forking, right? So if we did do all of our work on top of 3.5, and then in 2 years from now 3.6 comes out, we'd have to report our patches again. And then in 2 years later 3.8 comes out, we'd have to report our patches again. After going through that entire process that Fangman mentioned once, if we did that every 2 years, we'd give up at one point and say, you know what, this is too much work, let's just fork again, and we'd be stuck on our own internal branch. So, we put in the effort, let's take advantage of that and just stay current and relevant at all times. So that's kind of why we're doing it this way. Click again. Okay. So kind of how does this work? So when Fangman left off, we kind of had our notion of our patch set on top of open source 3.6. Obviously, that was a version of 3.6 at some point in time that we stabilized and we shipped into production. From that point on, we've basically just now taken our patch set and rebased it every month or so. Originally, it was every 2 months, and now every month, and hopefully we'll get that even smaller at some point. Just take that patch set and just rebase it on upstream. So basically, we're always taking just a certain checkout of master with our changes cleanly applied onto them, which sometimes takes some effort to rebase it and so forth. But that keeps things easier than having a branch that we merge in, because that becomes too easy to diverge and hard to merge back. And we have some internal tooling here to help make this easy for us. The other thing we're doing is we are regularly upstreaming our changes. So as we upstream our changes, when we rebase, it turns out that a lot of stuff that was inside our internal patch is now in upstream zookeeper for real. So it just goes out of our patch and falls away. So that's great. So we're minimizing our patch set over time. One thing that's not quite shown here is, of course, we are also developing new features as we go along. Those are kind of hopping on the top here, but eventually they get upstreamed, and as long as we're upstreaming our changes faster than we're writing new ones, eventually this will shrink over time. And so far that's been true. We've been, actively keeping up on it. The harder part is just really dealing with the backlog of 5 years worth of changes, but we're trying to that's why we're actively doing this. So up to this point, we've talked about our patches. What I want to talk here is kind of just high level what these are, so give us a scope of sort of what we've done. A lot of this has already been upstreamed and where we're going. So in total, we have about 60 patches we're upstreaming. Fangman earlier mentioned about 80. There's 60 we're upstreaming. Of the other, that's kind of like internal stuff that makes it work with our CI system or our internal stuff, things that don't really matter to be upstreamed. So there's 60 though that are totally just generally useful that we're working on upstreaming. Of those 60, we've done about 35 already. Actually, I think this number's wrong. I think we're like 38, 39 now. So we're more than halfway there, which is really cool. And obviously, I'm not going to go through 60 patches. So I want to break these into kind of groups, just to give an idea of what we care about. So the first is visibility. So open source Zookeeper doesn't have a lot of metrics. There's like 10, 12. When you actually run Zookeeper in production at scale, you're kind of blind. So one of the first things we learned years ago is we need to add a lot of metrics to figure out what the heck's going on. More fine-grained latency metrics, things like that. So the first thing we have done is exactly that. We've added about 100 metrics to Zookeeper over the last 5 years. One of the first steps of this was adding kind of a new subsystem that makes it really easy for us to just lightly add metrics anywhere in the system. Because we learned that if you make it easy, people add metrics. If you don't, they don't. So making it easy allowed us to get to this number, and sort of as we add new features, to always add new metrics with it as well. And these are like pretty fine-grained too, like not just a request latency, but things like, oh, here's the amount of time the request was spent in the prep request processor, in the sync request processor, in the commit processor, where you can actually find out, like, if a request is slow, why was it slow? And then maybe investigate that part of Zookeeper and fix it. So that's been a huge win. We've also worked on enhancing our server tracing, so we made it easier to add new server traces. This also, instead of it being written into a file, actually kind of gets exported out over the network to a process that runs in our box that then, in our case, kind of connects to our internal analytics store so we can look at that. But it could be reused. You could cook this up to something else. But it's a kind of a push model of tracing rather than just write to a file on disk and parse it later. So this was a huge win for us, too. Overall, I would say that the visibility features we added were probably the biggest thing. This would allow us to actually understand Zookeeper and make a lot of the other changes we've done. So these were a huge deal for us. I would say our second biggest win has been system protection. So one of the challenges with Zookeeper, right, is it's very easy to knock a Zookeeper over with thundering herds, with load spikes, with a bad client, and it just, you do too much work, a bunch of things start queuing, a bunch of systems kind of clobber up, and then Zookeeper basically is dead. Unless you come on and reboot it, it just dies. And we wanted to fix that problem. So we talked about 2 years ago some of the work we did in this area. We added request throttling to sort of limit the number of total requests in flight. We added connection throttling that limits how fast you can connect, which also limits effectively, indirectly, how many sessions you can create at a time. These were both helpful. Since that time, 2 years ago, we've done a lot more work. We've actually tried to extend this to be a little bit more fine-grained. So the last stuff was more global. Like, here's the limit at which Zookeeper falls over. We won't let you do that. Really, what we wanted to do is actually tie this more to clients themselves. So we've worked on adding client IDs and to actual clients. So when they connect to Zookeeper, we know who they are, and we can attribute load to them. And then we're also looking at extending that to do things like quotas and demand control. So hey, you're a client. You signed up to only do 100 writes per second. If you try to do more, we won't let you. And so that's something we're still actively working on, but this is going to be a huge win when we get it done. So performance. This, of course, there's always performance room in any system. Here's some of the highlights. So snapshot compression, pretty straightforward. We have gzip and snappy compression built in so that you can save on I/O right into disk for large snapshots. We have smarter write batching that we've added that allows us to be smart about how we write batches to the transaction log, and this was a huge win. I don't really have numbers here, but I know it was a big deal for us. We also improved the commit processor a lot. So Fangman mentioned earlier how the 3.6 commit processor improved mixed read-write workloads a lot, and it really did. That graph earlier was a huge win. But we found there were still some scenarios where things would be subpar and we could do better. There's actually two features, two specific things I want to call out. One is we actually improved write time for like heavy write workloads by about 20%. This is a pretty easy change. It turns out the commit processor in 3.6 has a dedicated thread pool to handle reads and writes. It handles, so you can do reads in parallel. It also issues writes to that thread pool. The problem is that you only ever can do one write at a time. So you were actually issuing a write to a thread pool, waiting for the thread pool to run, and then coming back to the main commit processor thread, but you're not getting any parallelism. So we changed the code here to actually do writes inline on the commit processor thread, and that's what gave us the win here. Basically getting rid of the context switching on the threads, because it didn't buy us anything. We also did some work to avoid what we call collapse, and that's easy for me to explain on a picture, which I'll do next. Basically, collapse is this issue here that there are certain workloads where if you have a heavy mixed read-write workload and something stalls, Zookeeper have a brief GC, there's a network stall, something like that, that causes your commit queue and the commit processor to queue up, it'll get into a case here where basically it can never drain the commit queue again. So this is a case here we have mixed workloads. The graph on the top here shows the write latency basically going up and to the right. So we got a backlog of commits. The new commit processor effectively favors reads over commits. And so once you get in this scenario, it will always be flushing reads faster than commits and can never catch up. So you never actually get your writes done. The bottom shows some code we did here to actually make it be smarter and adapt to this case and actually handle more writes versus reads. Basically, instead of being one write per n reads, you can now configure this to be m writes per n reads. And there's a few other minor changes too, but that allowed us to, yes, we do still spike, but then we actually recover after this event. So this was under a synthetic workload, but it's the shape that's kind of the interesting thing here, not recovering versus recovering. Availability, of course, is a big deal. Of course, Zookeeper is a highly consistent key value store for leader election, various other things. It's critical to most services. So we did a bit of work here. One of the big things we did here is there is some kind of worst case leader election time where the leader can kind of change its mind and say, oh, actually, it shouldn't be A, it should be B. And then there's some timeouts that sort of you wait until when you would the system would converge. That, in the worst case, was leading to 60-second leader election times in these corner cases. We did some work to optimize this to bring it down to about 5 seconds in these scenarios, which was a huge win. We also worked on something we call read-only observers. This is basically an observer that was connected to a leader, and then disconnection from the leader will still serve clients with stale data. So this sort of builds on the existing read-only Zookeeper server that's in Zookeeper, but it would automatically switch between read mode to read-write mode, or to read-only mode and back to read-write mode when available again. And this allows us to still be available, just not current when necessary. Reliability is a big thing. Of course, Zookeeper's record store, it's super important. So the main thing, we did a lot of bug fixes and little things here, most of which was upstreamed, but one of the big features we've done, and we'll be talking more about this later today, is a thing we call online digest checking. And this is work that allows us to basically, at any point in time, do end-to-end checking of guaranteeing that the data on a particular Zookeeper node is correct, it's what it should be, and it's also correct with respect to the quorum as a whole. And this is a really cool feature because it allowed it to find some existing bugs that were already in Zookeeper, really rare corner cases, but were there, and fix them. But it also allows us, more importantly, to move fast in the future, keep adding features, and not break Zookeeper, because we'll know from this if the new feature suddenly causes a digest exception. And we'll talk more about this, and Siog will in a little bit. Scalability, of course, as well. This is less about individual performance, but handling more clients, more watches, more observers. We worked on adding what we call scalable observers. This is basically the notion of allowing observers to follow followers. So right now, observers only follow the leader, which means you're stuck to the single NIC performance for the leader. We added this, and Brian will talk more about this in a bit. We also added a new watch manager, as Fangman alluded to earlier. This basically optimizes the scenario when you have lots and lots of watches. As a data point here, if you have like 1 million watches, it used to take 50 meg in the old watch manager, now it takes about 200 kilobytes. This is basically by using bit vectors and some other tricks. You use less data to store the actual watches that you're tracking. This is great for lots of watches. And then, of course, security. There's main 2 things we care about here. Zookeeper today was in plain text for the most part. We're working on server-server encryption and client-to-server encryption, and we'll talk more about that in depth as well very soon. So those overall are basically the patch set we have, the high level. So before I hand it off to my coworkers to kind of talk more about some of these areas in specifics, I kind of just want to recap on this whole journey itself, this journey and where we see Zookeeper today as a whole. So first off, right up front, Zookeeper is actually really awesome. And I don't just mean Zookeeper in general. I really mean like this whole thing where we moved to 3.4 to 3.6 and did all that work. While there was a big journey to do that, it, for the most part, wasn't drastic. It wasn't crazy. There's a lot of other software products I know where if you went from a 4-year-old fork to suddenly running on master, that it would be tragic, that you'd have bugs and things would break and all hell would break loose. And that didn't happen here. That's because Zookeeper, even on master, which is sort of some new thing, is still a really reliable product. It's still done well. So as a community, we've done a good job sort of sticking to keeping Zookeeper a reliable, safe, great system. So good job on all of us, and that's really cool. So I'm just excited about that and so forth. And also, the thing I want to say is just like it's a great thing for us to build all these new features on up too. So we built a lot of these features, but the commit processor improvements we did were on top of the new commit processor itself. That was a community contribution. That was a huge win. So there's just a lot of cool stuff still happening in Zookeeper even today. But with that said, what are some high-level things we think are open in Zookeeper, like open questions? What is missing? In addition to the stuff we talked about. We pulled our team a little bit, and here's some of the high-level highlights that we thought were interesting things that we still think we could do better at. Multi-tenancy is a big one. The demand control work we talked about earlier with client attribution and work shedding and so forth is part of that. But I think there's a greater room here for some kind of solution here to handle noisy neighbors and different people talking to Zookeeper, not overwhelming it. So something along that lines would be really cool to look into. More metrics, more visibility, better tracing, obviously, is always a never-ending game. So that's still another thing to keep working on. And there is some cool initiatives being done on that right now, too, to push metrics out to systems and so forth. Backups, there really is no generalized backup solution Zookeeper to back up the data somewhere else. Obviously, Zookeeper itself is great and keeps your data around, but what happens if for some reason you just need a backup? Right now, we had external stuff that just backs up from the files on disk. It'd be really cool to actually have Zookeeper itself have some built-in backup mechanism that also tied into how it does purging of transaction logs and snapshots and so forth. So you maybe say, hey, back up my data before you delete it, if possible, and things like that. So that's an open area. And of course, just validation. Fangman mentioned earlier about how we tested things by using our performance benchmarks and our fault injection. And that was really cool, but we still could do better as a community. We need a good way of, hey, if I write something new on Zookeeper, how do I know I didn't just break the world? It's a very complex system. We have unit tests. Unit tests are great, but really a good end-to-end performance test. There's a lot of work we could really do here to build confidence and allow us all as a community to move faster. So again, open area that we just think would be cool to figure out. We don't have the answers. Finally, I think there's 2 open questions. These are more food for thought. I just want to put in people's back of their minds that we can talk about later in the happy hour. First is, what's the plan with Java moving forward? Right now we run Java 9 in production at Facebook for Zookeeper. I suspect at some point in the future we'll probably move to Java 11 and 12 and 13 and whatever. I think it's interesting because the world's kind of switched a little bit, right? You have your older enterprise companies who, maybe are still on Java 6 and haven't moved to Java 8 and really want super, super stable. And they have companies like us where actually, if the whole company moves forward to Java 11, for example, and we're still stuck on Java 9, we're now actually the special snowflake. We're actually the ones who are now unsupported. So it's like the inverse of the enterprise problem, right? The further we stay behind, the less supported we are. So what's the plan there moving forward? Again, food for thought for the happy hour later. And then also sort of a general release plan question. 3.5 is coming up soon, which is great. But we just had this whole talk right now up to this point where we're saying we don't run 3.5, we run master, and we're going to keep running master. And so the open question here is how can this help as a whole, the community? So we run master at scale at Facebook. That gives us a lot of signal about Zookeeper, but that signal doesn't necessarily tell you anything about 3.5. Or if you make a 3.6 branch in a few years and we're running what is 3.4 at the time, it doesn't really tell you a lot about 3.6. So is there any way we can do here to sort of help this out? I don't know the answer. One thought we kind of threw around at one point is maybe it would make sense to have kind of two versions of Zookeeper. There's the stable enterprise version that comes every 2 years, and maybe there's a community release that is just like master a month after what Facebook ran in production. I don't know, crazy thought, but something we can talk about later too of like how do us moving fast and validating at a big scale, how can that help releasing stuff regularly to other companies that maybe don't have that but would like to run what we have? So open question. And that's all I have, and so now I'm going to hand it off to Ilya here to talk about security.
Hello. My name is Ilya Maikov, and I'm actually not a member of the Zookeeper team. I'm a member of a security team here at Facebook. For the last few months, I've been collaborating with our Zookeeper team on some security features. Let's see, how does this work? This one? OK. Yeah, so basically the goal that I want to get to is that all Zookeeper network traffic is encrypted with TLS. And as Joe mentioned, before we started on this, Zookeeper was effectively plain text on the wire. And we decided to break this up into two phases. The first phase is what we called quorum TLS. So this is encrypting connections between ensemble members. I actually implemented something first and then was notified, hey, actually there's a patch already. Zookeeper 236. So then after looking at that, we decided to throw away my implementation and go with, help move this patch forward instead. So we merged it into our internal fork. We tested it very thoroughly. We made improvements to it. We deployed it, and we reviewed the open source commit. So Zookeeper 236 has been landed as of, I think, a couple months maybe, or a month and a half, something like that. Yeah, let me just talk about some of the challenges that I ran into when adding security to Zookeeper. So you think, oh, what's the big deal? You just turn on TLS and you're done, right? Then we have like classes in the standard library that let you do that. The first challenge I'm going to talk about is the zero downtime upgrade. So we have a ensemble that we can't shut down the whole ensemble for any amount of time, right? It has to. Some part of it has to stay up always. Well, we can shut down some of the machines as long as quorum is maintained. So here we take down the leader, and then we bring it back up. This leader switches to this other machine. And now this green machine, ZK1, is now able to speak TLS. Right, so it can speak TLS, but this other machine it's connected to cannot speak TLS. So then what protocol do I speak on the wire here? Well, it's not clear, right? You can't speak TLS, but you can't speak not TLS. So the logical conclusion is you need to support mixed clusters where some of the connections are encrypted and some of them are not. So how do we do that? By the way, this part of the talk it's kind of at the high level, but it gets a little bit technical. The way we do that is we accept both TLS and plain text connections on the same port. So we call this port unification. And every connection starts as plain text and then maybe upgrades to TLS. So we have a new class called the unified server socket. And its accept method returns another new class called a unified socket. And then this thing, essentially, as soon as you need to do some I/O on it, or as soon as you want to actually use it, it'll read the first 5 bytes of data coming from the client and check, does this look like the start of a TLS connection? Does this look like a TLS handshake? And if yes, then it basically magically upgrades itself to an SSL socket. And if no, then it remains a plain text socket. There's a landmine here. You can't block the accept thread when checking for TLS, so this read has to happen. This read has to happen on a different thread, not on the accept thread. If you try to do it on the accept thread and you get a bad client that just connects to you and then never sends you any data, then you block your accept thread and then you can't accept new connections. We actually ran into this bug while testing this and had to fix it. Also, it's kind of tricky to make it completely transparent to the user. You basically don't want to force the users of this API to do the read themselves, because if you do that, then you're probably going to forget it in some code path. So you just want it to kind of happen transparently. And like many problems in computer science, it's solved with a layer of indirection. So let's see, how would we actually upgrade a cluster to TLS? You need a couple of rounds of restarts. So the first restart, you're going to enable port unification. Then you're going to restart again and enable outgoing TLS connections. I have a little legend at the bottom. And I'm going to ignore the fact that the leader changes, potentially. So I'm just going to pretend that the leader never changes. So first, we upgrade this guy to turn on port unification. We do that with all 5 machines. So now every machine in this ensemble is able to accept both TLS and plaintext connections. But all of them are actually still speaking plaintext on their outgoing connections. So effectively, nothing is encrypted. And the second round of updates, you actually restart your machines and say, OK, now that everybody can accept TLS, we want your outgoing connections to be TLS. And then after 2 rounds of restarts, you're good and everything is encrypted. And these are sort of the regular ZAB connections. The election port connections are not shown, but we do the same thing for those. OK, second challenge, reload certificate files. So at least in our infrastructure, we have some way to manage certificates on disk and manage private keys on disk. And we might not want to have very long-lived certs, right? We might have certs that refresh, whatever, every day or every week. But a zookeeper server could be up for much longer than that without restarting. So we need to be able to reload the private key insert when it's updated. However, Java's SSL server socket does not let you do this. So if I have a cert that let's go back. So I have a cert that's being used by an SSL server socket, then it's expired, and I have a new cert, and I want to plug it in somehow, but there's no way to do that. I would have to tear down the socket and create a new socket to use the new cert. So the solution is kind of a hack, but it totally works, and that is to use the unified socket even for strict TLS mode. So this part of the picture is the same. And then if the connection looks like TLS, then we upgrade to an SSL socket. And if no, then we just close the connection. So even if you're sort of in strict TLS mode, you can still use basically the same code as you do for port unification. And the reason this works is that the SSL context is configured right here when you do this upgrade. And so you can just use whatever is the latest cert and private key that you've loaded from disk at this point. One issue that we ran into was high CPU overhead due to basically due to the encryption. We ran into this on Java 8. It turns out that if you use Java 9 and use AES GCM, then this goes away, at least on Intel processors, on modern Intel processors. The reason for this is that Java 9 actually properly implements AES-NI instructions and basically accelerates everything with hardware, whereas Java 8 does not. So there are a few patches on top of Zookeeper 236, or I guess on top of master. There are 5 JIRAs that I opened, but I combined 2 of them into one patch because it was hard to split them up. So I ended up with 4 pull requests. Actually, the first one landed upstream yesterday. So the one that adds PEM support and test improvements, number 678, is already landed. And the other 3, 679, 80, and 81, add things like we fix bugs in port unification that makes it actually usable, and we added the reloading of certificates on changes, and then added some extra options for configuring the SSL behavior, such as if you want your clients to, if you require your client to present a cert or not, and things like that. And those are in review, and hopefully will be landed soon. Yes, so this has been running at Facebook in production for over a month. So it is pretty well battle tested at this point. Yeah, I don't think we've run into any issues. So phase 2 is client TLS. So this is adding security to the connections between clients and Zookeeper servers. So there are a couple of challenges here that I'll talk about as well. So one is handshake overhead. So we might have ensembles where many thousands of clients are connected for each member of the ensemble. And if a leader changes, then all the clients disconnect and reconnect, right? So when this happens, that arrow is supposed to point to the other one. Oh, maybe not. Let's see. Yeah, and actually, this is correct. Yeah, so leader changes, everybody disconnects and reconnects, and then we could end up with sort of many thousands or tens of thousands of TLS handshakes in a short window of time. And TLS handshakes are expensive in terms of CPU, because you're doing a bunch of asymmetric cryptography operations, and they're also slow because you are doing multiple network round trips. So one solution to get rid of to mitigate somewhat the handshake overhead is to use something called TLS tickets. So at the high level, I'm not going to get into the details too much, although I provide the links to the RFCs that explain this. So at the high level, you have a couple servers, and you want to be able to resume a session from a TLS session connected to one server. You want to be able to resume it on the other server. And the way you do this is the servers share a key, let's call it K, and then the server creates something called a ticket, which is basically the session state encrypted under this key, and then gives this ticket to the client. And then if the client disconnects from one server and connects to a different server, then the client can pass the ticket along, and then the second server decrypts the ticket, which it can do because the two servers share the key, and then restore the session state from there and resume the session without doing a full handshake. Let's see. What's going on here? Yeah, and so there's a RFC that describes how to do this in TLS 1.2, and it's actually part of the base protocol specification for TLS 1.3. So this is what we want to use, and in fact, we use it already in other places that are not Zookeeper at Facebook. One problem is that NETI3 doesn't support it. So NETI is a networking library that is one of the options for the client-facing networking in Zookeeper. So let's upgrade to NETI4. Well, unfortunately, many APIs have changed between NETI3 and 4, and some of the sort of ways that you even do things in NETI have changed between them, and the upgrade path is kind of non-trivial. I found a blog post where some engineers from Square described how they upgraded a reverse proxy, I think, from NETI3 to 4, and it took them 4 months. So it's not necessarily easy. Also, if you want to use tickets, you have to use NETI4 with the OpenSSL transport, which means you have to use JNI, which maybe not everybody wants to do, and it kind of complicates your deployment a little bit because you have to make sure you include, native libraries along with your Java code and so on, with your jars. But anyway, the pull request for the NETI3 to 4 upgrade is up. It is pull request number 669, and there's a Jira. So hopefully we can get that in. I just landed this internally to our fork a couple days ago, and we're going to start testing it very soon, sort of at scale. We've tested it. We've done some smaller tests, but not at scale yet. Yeah, and I need some help to get this reviewed and get it in. And then the other challenge for the client to server TLS phase is we just have heterogeneous clients. We have many different client code bases in different languages, and sort of it increases the surface area of how many things we need to test and modify. So obviously that's more chances for bugs to creep in and so on. And this is a work in progress. Some future work that I think we'll be able to do that will kind of build on top of this. So one is TLS-enabled authentication and authorization. So basically, we already have a framework for this at Facebook where we can make authorization decisions based on certificates that we issue to all of our services and all of our clients. And I'd like to bring that to Zookeeper so we could say something like, only whatever members of this particular team can connect and write to this ensemble, or only these services can write to this ensemble or read from this ensemble. And this will potentially require adding some sort of interface, authorization interface to Zookeeper, and then extending it with some Facebook-specific code that we would not open source, but other companies could implement it for their own use cases. Joe mentioned earlier we have metrics and quotas based on client identities. So right now those identities are easily faked, like the client just says who I am, but the client could lie. Once we have TLS and we have certificates, the client wouldn't be able to lie anymore because we could get that identity out of the client's cert. And also TLS 1.3 support, which I think would need Java 11 and 95, although I haven't verified this. But eventually we would want to go to TLS 1.3 because it's basically better in every way than 1.2. And then finally, because I'm not a member of the Zookeeper team and I don't typically work with the open source community, I wanted to share some thoughts on working with open source. So the first one is that to me, it felt like the Zookeeper community moves relatively slowly compared to how fast we move at Facebook. It's much easier for me to sort of get some code reviewed and get it landed internally. And there's definitely some resistance to large pull requests or major changes, which is actually a good thing. So initially, I had this big stack of a bunch of changes, and I kind of squished it all into one pull request and put it up for review. And people basically told me this is 5 different features in one pull request. You need to break it up, and that makes sense. A part of the reason that I had that big staff is that the workflow we have internally at Facebook is a little bit different. So we use the system called Fabricator, and we use this workflow of stack diffs on top of master, which doesn't map very well to GitHub pull requests because it's hard to stack pull requests on top of each other. So internally, I can sort of put out one diff, and then I can start working on the next thing while that's been reviewed, and I can kind of stack as many as I want on top of each other. And then once the whole thing is reviewed, I can just land it all at once. I can't really do that on GitHub as far as I know. And I need a +1 from a committer to merge a pull request upstream. So it's kind of we have a committer at Facebook, Fangman, but the +1 on a bunch of Facebook code should probably come from somebody else who doesn't work here. So it sort of means we have to build consensus. But I also thought it was a pretty good opportunity to sort of get some open source cred, and it's a chance to do good in the world and help everybody secure their Zookeeper clusters. So I'm really glad that I have this chance to work on it, and I really enjoyed it. Next is online consistency checker, Suyog. Thank you. Are you using this one or?
No, that's fine.
Yeah.
Hi everyone, my name is Suyog. I work in Zookeeper team, and I'm going to talk about online consistency checker, which, as you would guess, it's a framework that checks that the data is consistent across different servers. Let me first start by an obvious question. Why do we need it? Suppose you are working on some cool Zookeeper feature. Currently, there is no good, easy way of making sure that you're not introducing any consistency issues. Our experience shows that you have to do a lot of testing, go really slow, and still something might slip. This is an example of a bug we had in the 10db. And it did not even be something like a new feature. Even if you're doing some routine thing like rebasing on open source master, the merge can get really tricky, and you would like to have something watching over your shoulders, making sure that nothing slips. And this feature is intended to be that someone, at least as far as consistency is concerned. You would say, isn't it something that Zab is responsible for? Well, not exactly. Zab only ensures that the persistent state on all servers is identical. There is significant non-trivial Zookeeper code that runs on top of Zab, which is not covered by the guarantees. And if you think Zab is a real code and can have its own bug, the slide lists a couple of bugs we fixed in Zab in the past. As you would know, Zookeeper also has CRC checks that protect our transaction and snapshot files, but from one particular type of issue, local disk corruption, and doesn't give us end-to-end protection. From this, it's not surprising that we are obsessed with end-to-end consistency checking, and that's our primary goal of this project. When I say end-to-end consistency, what I mean is that we want to be sure that in-memory state of all servers is identical at any given logical time, also known as ZixID in Zookeeper. It also helps to do this detection in real time, because if something is wrong, you want to know about it as soon as possible, and doing it in real time allows you to do some automatic recovery in future if you want. With this, let's see how it is implemented. We do consistency checking in 2 places. Firstly, during a steady state known as a broadcast, and secondly, when the Zookeeper server starts, a load time. Let's first see how it is done during the broadcast. For simplicity, let's assume that Zookeeper only processes one change at a time. So conceptually, when leader receives a change, it applies it to its own data tree, computes a hash or digest over the entire content of a data tree. It sends that digest in a prepare message. Follower appends the message to its transaction log, and it also persists the digest. When follower receives commit message, it applies the change to its own data tree, independently compute the digest, and compares it with the one data sent. If they match, you know with high probability that their content is identical. If they don't, you have a real-time inconsistency detection. Well, that's about it conceptually. But as you would guess, real implementation has to do with few challenges. Firstly, it's not feasible for us to compute digest or the entire tree, entire content of the tree, and we have to do some kind of incremental computation. For that, we use an algorithm called add hash. In a nutshell, add hash defines digest of a tree as sum of digest of all the nodes divided by some integer. When I say digest of a node, it is the content, the metadata, and the path. So as you see, the digest of a tree only depends on its content and not the way it is constructed. So this allows us to do incremental computation of digest. The second challenge is zookeeper doesn't really deal with one change at a time. You have multiple outstanding changes in a prepare request processor. So this is actually easy to deal with. Instead of applying a single change, we compute digest with applying all preceding changes and the current change. And as you would guess, we don't actually apply it. We just pretend that we apply and compute the digest. So it's done in incremental fashion as well. As I said before, the second place where we do the consistency checking is doing a load. So here, the primary challenge we have is the zookeeper snapshots are fuzzy. The way we deal with it is, after saving a snapshot, we look at the current Zix ID of a data tree and save that as the last Zix ID in a snapshot. When you load the snapshot, When you load the snapshot, we don't immediately start checking for digest. We wait till enough transactions are replayed, and the data tree Zix ID equals the last Zix ID we saved during the snapshot save. When that happens, we know for sure the data tree is now non-fuzzy, and it is safe to start checking digest. After that, as we apply transactions to data tree, we compare the digest saved in the transaction with whatever is the current digest in data tree. So this is essentially how it is implemented. Let's talk about how the production rollout. Before you can roll out any new feature, you have to make sure that it's compatible. The feature is behind a flag, and it is, of course, backward compatible. The feature is designed to be also forward compatible. So you can run the feature in the production for a while, then replace it with some older version of Zookeeper, and that version should have no problem reading the digest-infested data. The digests themselves are version. So in future, if you want to add some new field in metadata to digest, or you want to change hashing algorithm, all you have to do is bump up the version, and the framework will be ignoring the digests that do not match versions. We have rolled out the feature to majority of our production fleet, and we expect that we will finish the rollout sometime this month. So yeah, we will be having it running up and running 100% by the end of this month. And it has actually already helped us catch 4 of the existing consistency issues in Zookeeper, and I hope it would help us catch any new bugs, and as Joe said before, it will allow us to move fast and with much higher confidence. Thank you. I'm handing to Brian for scalable observers.
Hello. So I'm Brian. And when I was first joining the team and considering joining the Zookeeper team, this particular feature was being presented to a room very much like this one, though at the time it was entirely conceptual. So between then and now, we've taken that concept, we've actually built it, we've deployed it, it's running in production quite happily. And let's talk about it. So observers, not everybody uses them. What they are is a very nice way of taking high client load and reducing the impact on your voting quorum. So there are server processes that look a lot like a peer, but they don't participate in voting. They just purely take commits as commits are made by the central quorum, and they serve as almost a form of cache for client traffic. But you can have a problem. What happens when you start to get lots and lots of observers? Your leader is struggling. It's got to support all this extra load, it's got to support the effort on the NIC. And meanwhile, it's got to keep doing its standard work as a leader. This can't last. Put more observers, eventually things are going to fall over. So the idea is, why don't we just spread that load out across your core? We're going to train all of the followers to be able to serve this traffic just the same way the leader can, and they're going to be able to support their own mini observer fleets just the way that the leader would. We thought at the time maybe we let observers also serve as these sort of forwarding agents, but that seemed unnecessarily complicated. You can imagine building topologies in which the leader propagates to observers, which propagate to observers, which propagate to observers, and rather than try to reason through all the bizarre corner cases that could come up, we're just going to let observers follow followers or leaders. So, built it. It's great. What are some common problems that might arise? Well, what happens when a follower dies or restarts? The observers move somewhere else. Now, that's great if what's happening is some sort of system event. But what about when you're doing a rolling restart or some kind of upgrade and you're expecting people to die? The observer could be punted at this point from follower to follower to follower to follower as you're just rolling through, and they could be seeing this continuous series of failure events and then pushing that on to your clients who then perceive disconnect after disconnect. Not great. So our reaction to this is to really tune the retry times to make sure that observers are aggressive in finding people to follow, and then the load on the client then, or what the client perceives as outage time, is minimized to a fine degree, or as fine degree as we can. What keeps the observers in balance? There are pathological cases with our initial conception where, despite your best effort at spreading your observers out over your fleet, successive restarts could just pile all the connections back onto one server again. And you're right back where you started, where now you're incredibly vulnerable, and if that server goes down, well, assuming that it was able to serve that traffic, now you have a giant impact. What we did is we added JMX endpoints, effectively, that allow us to issue, as admins, effectively marching orders to the observers. So we can tell followers, go ahead and shed some observer connections, make them go somewhere else, and we can tell observers, you're in the wrong spot for the load that we see, please go somewhere else. And in this way, anyone who accumulates far too many connections, they can be kept sort of in check and within normal operating bounds. So this code is up. It's available. We've offered it to the community. 3.1.40. Pull request is open out right now. It's 30 files that have changed. It's about 2.5K worth of added code. So it's a big one. But please do go take a look if you find this interesting. Add comments. Give me a hard time. I will fix it up. And hopefully everyone else can share what will be very smooth observer traffic in the future. Thank you. Up next is Violet.
Hi, my name is Ivailo. I work also on the Zeus team. Zeus is synonymous with Zookeeper at Facebook. And I'm going to give you a brief update on the work that we've done on the Zookeeper client's front. When you look at the landscape, it's really like three main languages. There are other exquisite birds on Facebook, but these are the primary three languages. When you look at Java, Curator is really well established with the community, and people are happy with it. When you look at Python, Kazoo and Kazoos are also really well established. When we look at the C++, the main client is the old C client that comes with Zookeeper, and we've done quite a lot of work to build on top of it and later replace it, and I'll talk about it. So the work that we've done, and it's already productized, is that we build a brand new C++ Zookeeper client that is based on the modern C++ structure, and it's also Foley based. So Foley is an open source library as well. And one of the important features that we added is, like Joe briefly mentioned about it, is that we introduced the client ID. Every single use case has to create a client with a client ID, and the client ID is attributed both on the client side as well on the server side. The server, every session ID has a client ID. So this has been a tremendous help for us when you try to debug issues with, especially with shared ensembles, and you try to figure out who is like responsible for the load increase, et cetera, et cetera. But it's also very helpful for dedicated ensembles, because you can have like a single team owning the ensemble, but really like you have different scenarios that can be attributed different client IDs. We've added a lot of instrumentation for all the important metrics, and this also is a great help when you're debugging issues. Very important for us is like to be able to track changes whenever we do maintenance, servers go out, servers being replaced. This has to be tracked automatically without running into a difficult situation where the connect string is no longer with any valid hosts. So this has been done through our service discovery. The set of zookeeper clients on C++ also has like a reconnecting client that will persist the connection, and it will create as many as base clients necessary just to persist. Now creates a difficult situations with moving forward with ephemerals. Obviously, when you recreate, ephemerals go away. We have moved and created all the high-level recipes like mutex, semaphore, Lido election, and these are like all part of the C++ zookeeper client. And all the retry recipes, especially when you have like a network exceptions and you have to retry different requests. Now, the very first phase, this was entirely based on the zookeeper C client, but we've gone a step further than that. And we've completely replaced the C client with a brand new implementation that is done from scratch, following the same philosophy. Again, fully feature-based, and it's the most important thing is that now we're completely independent when it comes to the C++ client from the C client. And plan is that we will gonna open source and everybody will benefit from it. Thank you very much. And Norbert is next.
Thank you. Oh, no, I have microphone. So, hey, everyone. My name is Norbert Kalmar. I'm going to have a presentation about Zookeeper 3.5. Yeah, Fangmin mentioned 3.4 and 3.6. I'm going to mention 3.5. Yeah. So a little bit about me. I joined Cloudera in April, so I've been working along the open source community for about half a year. I'm quite new. I work on Java backend and middleware stuff, but that was closed code, banking and aviation, as you can imagine. So why 3.5? 3.4, the first release was about 7 years ago. The 3.4.6, a lot of companies using that. It's more than 4 years old. And even the first release of 3.5, which was the first alpha release, was more than 4 years ago. So it's long time due that we release stable 3.5. For example, Curator is already using it since 3.0. It's the hard dependency which was released last year, the Curator. Already running in production systems, a lot of companies using 3.5 or even the chunk. Facebook's using 3.6. There's a lot of new features that, of course, hasn't been backported to 3.4. For a long time, it's been only bug fixes. And a lot of performance and stability improvements, the others have mentioned. I'm going to also mention some, like dynamic reconfig. You don't need a rolling restart to change the configuration of the Zookeeper nodes, or support for local sessions. There's also some performance improvement, take off some load of the leader. SSL support for atomic broadcast protocol has been mentioned. Watches removal, There's also new Z-node type, container type. It's going to be deleted once all the childs are gone. We have TTL nodes. I think Hive, for example, is using it for session tracking, but it keeps updating. And after a while, get child gets huge, and we run in the infamous what is it? Yeah, max buffer. We have a lot of issues with that. So TTL nodes are easy to help. It will automatically delete after some time. 4-letter word deprecation in favor of Jerry. Yeah, so we have 4-letter words, but it's not too secure. In 3.4, it's been used a lot. In 3.5, it is planned to be deprecated, and in 3.6, it will be removed altogether, and it will be replaced by Jetty. The Maven migration is in process, so we're going to move from Ant to Maven. It's been received quite good by the community. We can have better better manage the project itself, better dependency management. The code will be more structured. We have a lot of hacks in the end. The directories itself is not well structured. Maven is here to help, and other Hadoop components are almost everything is running on Maven. So documentation and website converted to Markdown. It's been committed a few days ago. It's being finalized. Maybe it's even finalized on the chunk 3.6. And yeah, the Jira speaks for themselves. So since 3.4, there are a lot of resolved tickets, a lot of new features, improvements, bug fixes. Of course, bug fixes has been committed to 3.4 usually, and other contributions. And of course, this is thanks to all of you guys here. So yeah, I just put up some people, of course, many others. So thank you all, and I hope everyone keeps contributing. And one more thing, you guys mentioned the release processes. After releasing 3.5 soon, stable 3.5, we plan to move faster and probably even half a year till 3.6. Maybe that's too optimistic, but definitely faster than 3.5. It's been too long. So yeah, thank you. Who's next? Oh, Michael.
Hello? Okay, cool. So I realize I'm now the only barrier between you guys and happy hour, so please bear with me. Okay, so let's get to it. Today I'm going to present Zookeeper at Twitter. My name is Michael Han. I'm a software engineer at Twitter. And my team basically owns a couple of core services at Twitter, including Zookeeper. So the motivation of this presentation is to basically share with the community of basically like what's happening with regarding to Zookeeper at Twitter, and what's our use cases for Zookeeper, and share some lessons and experience we've learned to operate Zookeeper at Twitter scale, and finally what we're working on. So, and also, although it's me who's presenting, but the content I'm presenting is basically contributed by many people over many years. So the name is too long, so I'm not listing them here. Okay, so this is actually the first slides, but okay, so first the current status. So first of all, Zookeeper is an indispensable piece of Twitter's platform infrastructure. So what does this mean? So this has several meanings. So first of all, Zookeeper is really one of the fundamental service, which means that it's really one of those few services at Twitter where it has no external dependencies, because it's really the lowest level or the core of the many of the systems. And so this also means that the expectation of the Zookeeper at Twitter is basically it must be very reliable, it must be available, always available, because if zookeeper is down, then many systems will have problems. So that's like why I'm also cading with my teammates, like if we do a good job, then we should have basically zero visibility, because people should not notice us at all. The other meaning of this is, like zookeeper is, for Twitter at least, zookeeper is hardly can be replaced by a different technology. So as we know, there are great piece of software developed these days, like etcd or Consul, for example, which basically aiming at solve a similar set of problems as zookeeper. And I think the community can also like learn lots of new design concepts or some of the cool features that develop on those systems. But when we're talking about the zookeeper, we are not just talking about those features or the server side of things, but we are also talking about the ecosystem or the APIs. So as we know, like Twitter is basically, a majority of the Twitter's backend stack is based on JVM. And we actually accumulate lots of experience on operating backend services on top of JVM at scale. And we have like great teams which actually working on the JVM and help us to tuning the JVM to make sure the services are scalable. So those type of experience are kind of hard to replicate, if we want to move to a different technology. And also, for those piece of technologies, it's not basically like offering the significant advantage comparing to zookeeper in terms of performance or features, for example, at least for the use cases we care about. So currently, regarding the environment of where zookeeper is running at Twitter, so currently the zookeepers are running. So we are running zookeeper on the bare metal hardware in Twitter's data centers. So this is just pure historical reason, but there's no technical difficulties on running zookeeper in a container environment, for example, on Mesos or Kubernetes or something in the cloud, basically. And this is something actually we are actively exploring and working on. Next is about scale. So the total number of instances or the server hosts at Twitter is about less than 1,000. So this is definitely, I guess, to my knowledge, not the biggest scale, excluding Facebook. So I know some companies probably they operate at a similar or bigger scale. But this is definitely not small scale as well. So it poses some interesting challenges for us to actually, how to operate such a large fleet of zookeeper servers with a really small amount of resources. Because our team is really, really small. So we own everything from the development to the operation as well. So in terms of the data scale, the data stored on zookeeper is basically the median value of the number of zenodes is something like millions. And we do see we do see in some zenodes the bytes of the zenodes is well exceeding the default root max buffer size, which is 1 megabytes. So in terms of workloads, we have read heavy. So primary workloads of our zookeeper servers are read heavy, which I guess is pretty expected because that's what zookeeper is best for. And we definitely also have the mixed read-write workloads as well. So next, I'm going to talk about use cases, and I think this is where things get interesting. As we know, zookeeper has a fame of being the grandpa or the king of the distributed coordination. So that's what the best use case for zookeeper is for, based on our experience as well, which is distributed coordination. And also, we use zookeeper extensively for leader elections in many of the use cases. And also, zookeeper is used for store critical metadata where the use cases require strong consistency. So I'll go through each use case and provide some concrete examples because I think that will make things interesting. So first, about distributed log. So to give a concrete example of distributed log, I want to provide some context information for one of our biggest customers in this case, which is something called distributed log, which is a Twitter project that provide the abstraction of a replicated log service. So you can think it's something like Apache Kafka or For example, the log device Facebook open source pretty recently. So the distributed log has the abstraction of streams, which is basically like the logical entity for the log. And for streams, it allows like multiple writers to write to different streams at the same time. But we are not allowing multiple writers to write to the so we allow multiple writers to write to different streams, but we are not allowing multiple writers to write to the same stream. So how do we do that? We basically use the zookeeper as a log. So if a writer wants to write to a specific stream, it has to acquire the log first. And also similarly, I think in distributed log we also use zookeeper for sequence generation. So as I just said, the abstraction of the stream, so for a single stream, it also contains many abstractions which called log segments. So log segments is basically the minimum unit of the actual physics bytes where your write will go to. So the each log segment has to be assigned a unique like log sequence number, which is what we call it. So and we use zookeeper's sequential node to basically get a unique number and then assign that to the log segment. And the next use case is about the change notification. So change notification, we have some concrete use case. One example here is our configuration management system basically use this feature, like the water feature in Zookeeper to update the configuration on Twitter's data center servers. So we have something called Twitter, which is a daemon that's running on every machines of the Twitter's data center. And what Twitter does is it's basically watching a znode or a subset of znode that's belong to like a sort of a configuration data tree. And when the znode changes, a watcher will be fair, and Twitter will actually execute some customized function or code. And in this case, Twitter is executing pulling down the configuration and then activate the configuration for some services or like some generic configuration change for some websites, for example. So this is about the first big type of use case, distributed coordination. And the next big use case is the leader election. So we use leader election for Mesos, which is Twitter's computing platform. And we also use leader election for basically a set of Hadoop projects. So we also use Kafka, and Kafka use Zookeeper for leader election for the broker. And also HDFS name node use Zookeeper for leader election for the high availability setup for the name node as well. And there are some other things like previously there were Twitter used Storm, and then now Heron both use Zookeeper as well. The final use case is we use Zookeeper to store the critical metadata information. And this use case, I think it can be categorized to some sort of like configuration management for a distributed cluster or service discovery inside a distributed cluster. So one concrete example here is Manhattan, which is Twitter's in-memory key value store that store lots of stuff for Twitter's like tweets or something else. And we use Zookeeper here to basically store the entire topology of the Manhattan cluster. And each node in the Manhattan cluster basically use this information to get awareness of the other nodes inside the same cluster, like their status, and some metadata around the data range, the data mappings, like how to find the correct node to issue a request. And we also use Zookeeper to store the metadata for our previously mentioned distributed log stream metadata, such as how many log segments a single distributed log stream contains, and how what's the transaction ID associated with the stream, or what's the biggest transaction ID associated with stream, things like that. And finally, the big use case, I guess, which probably there are lots of similar use cases outside Twitter as well, is to use Zookeeper for service discovery. So our experience on service discovery, however, is like Zookeeper is probably not the best or the ideal case, just for itself to serve the service discovery, because really service discovery is like an end-to-end problem. Because if you think about it, it's kind of like Zookeeper is a CP system in the context of CAP, right? And service discovery, in some cases or in most cases, you would rather prefer the availability over the consistency, because if if you don't have like a really consistent service discovery problem, it's probably not a big deal. But if your service discovery system is totally unavailable, well, at the same time, assuming like a partition happens like between some of your data centers, but the service can actually talk with each other within a single data center that's got partitioned away. But in that case, if the service discovery is totally unavailable, then those services can't talk with each other. So this is obviously not ideal. So how to solve this? So we similarly, as previously, I guess someone mentioned, as like every problem in computer science can be solved by adding a layer of indirection. So here we add another layer, which the clients, the service discovery clients directly talk to. So this layer basically serving as a naming service. And then it uses a Zookeeper to store the source of, I would say, the source of hint for all the services. And because of this layer of indirection, it's much more flexible, and also it's much more a scalable solution as well. So some history of Zookeeper at Twitter. So initially, I guess we started with the upstream stable version, which is 3.3 or maybe 3.4. And then we forked 3.5 because there's really great dynamic reconfig feature that really saves a lot of time on operation. And the majority of the major work took place in that time is the team tried to add the rate limiting or throttling control, or probably something called on-demand by the Facebook terms. So we did that by using Finagle, which is Twitter's RPC library. And Finagle internally was also using Netty. So that feature was not very successfully landed on production environment because like the Finagle style programming is basically reactive style programming, right? So it's like asynchronous everywhere with the abstraction of the futures and promises. But the Zookeeper architecture is more like log-based traditional programming mode. So they didn't fit nicely with each other. So I guess that's why the patch is currently not in use on production. But I think there are definitely some promising directions to look at. If we can somehow make both fit together. And we also have many internal patches, which I'll talk about in my next slides. So after that, we basically rebased to 3.5.2 alpha, I guess. And we ported some of the internal patches developed previously, and also we selectively applied some of the upstream patches to this fork. So I want to mention two outstanding upstream patch here. One is 2024, which is the improvements over mixed read-write workloads. It helps a lot, but make sure I think there's a follow-up fix, because there's a bug there, which reported by Ryan, who previously worked at Twitter. So we have an internal fix that fixed the issue, and there's an upstream fix associated with this as well. So if you pull down this patch, make sure to pull down that patch as well. And the other patch is 26.7.8, which I believe is about reducing the quorum synchronization time after redirection by not taking snapshot in certain times. So this also greatly helps us in cases where we have a big data tree and then we have redirection, and then it took really long time for the quorum to recover because the snapshot takes too long to do a snapshot. So similarly, this patch also has bugs, and there's a follow-up fix for this patch. So I think that patch basically links to this 26.7.8 JRA. So make sure to pull down both patch as well. So and currently we are actually rebasing our internal forks with trunk version, which is 3.6. And I think the work is almost done, and we are rolling out to the production, and hopefully it'll be finished in the next few weeks. So something about our internal patches. So currently we have about 15 internal patches. So most of these patches actually are around, around the area of improve the operationability, because we are a really small team, and if we get paged in the middle of the night, so what do you want to know? I guess the first thing we want to know is what's happening. How do we debug the issue, right? So for such case, to really get insight into what's happening, it's really important to have lots of metrics around around the various aspects of the system, and also it's good to gather like lots of metadata, so you can actually correlate the metadata together and to discover, basically to discover some useful leads for the incident or for the crime scene, for example. So here, like we have the simple metric system where we basically have a matrix subsystem where we define matrix types like counter and gauge. I guess that's the only matrix type we have. And then we instrument the code base a couple of places like to collect some of the data, and then we publish this matrix data using Finagle stats receiver interface to Twitter's observability stack, which is Twitter's in-house sort of monitoring system or the visibility system. The matrix data is basically stored in some sort of a time series database, and then they have a really nice UI that you can query with some customized query language that can show you, what's going on, which is really cool. And also, besides the metrics, we also capture some more metadata here, something like client ID, which Facebook teams also talk about. So we also do that because when something goes wrong, we want to, or when a certain set of clients abusing Zookeeper, we definitely want to point it to the client. So the only way we could do that is to basically have a client ID associated with the request. And also, we have something like, when the connection disconnect, we also log some context information of that client. So that's really helpful because recently we have the issue on production environment where some of our observers simply like are out of memory or garbage collect from time to time. So that issue turns out to be we are leaking some connection objects because the connection objects was used as a watcher key in the watcher map, and because the data tree is like the GC root where it can be garbage collected. So, and it happens to be that that connection has some like large byte buffers because the operation like we captured as a context information here indicates like it's a get children call with like lots of children's, like the payload is something like 10 megabytes. So like you can imagine like this would really like create lots of GC pressure. So we found out that we find out this by basically analyzing the heap dump. But if we don't capture this sort of information, it's really hard to really figure out what's going on. And the other thing we capture here is request status. So we're basically sampling and picking up the top key most frequently requested paths. I think this is also pretty helpful, when we want to blame some clients to sending too much traffic to Zookeeper. So besides all of this, we have lots of patches around the tooling. So some example including the backup. So we have some backup patch where it's actually a pretty relatively independent module of Zookeeper. So what it does is basically, it's like a special observer, but what it does is it's just get the data and then send the data back to HDFS where we store the backups to. We also have a tool called snapshot compare. So what it does is it's basically compare snapshot and find the difference. So this is pretty useful in cases where we want to basically figure out the trending of the data's growth or the data decreasing. So this is useful in cases where some clients might sending lots of traffic, but for some reason we didn't capture the matrix that can pinpoint to that misbehaving client. So in this case, we can just analyze the snapshot between the snapshot in different point of time and then figure out like which path or which client is basically sending too much traffic to Zookeeper. And we also have tools to remove the JNode like recursively and in batch, high performance remover. So in terms of operation, I think still it's all boils down to capture as much information as you could. So we have a matrix in these categories like the request latency. We capture the request latency, the query per second, the request size and type. So these are request status. We also have like capture the server status, like the process queue length, the packet sent and received, fsync, and ZXID. And something related to data tree status, and finally the JVM stats and the network stats, which are also helpful because the more data you capture, the more you can correlate together and then figure out, if something goes wrong, then you have more data to at least support your theory of suspicions of what's actually causing this. So backup I already talked about, and the topology change. So we use dynamic reconfiguration to do the topology change because we are running on bare metal hardware, and bare metal hardware actually, we really see like some disk, like some hardware failures on the disk or some kernel failures from time to time. So that makes us to have to basically remove that bad host and then add back to a healthy host. And we use dynamic reconfig in this case. And it's really, really, really great feature and great tool. And I can't imagine without such a feature, like we can operate such a large number of zookeeper hosts on such a scale. So here is what's happening regarding to zookeeper at Twitter right now. So currently, as I said, we are rebasing the our internal fork with the trunk, and it's almost finished, and we are rolling out to the production. And at the same time, we are trying to basically trying to upstream some of our internal patches to the community as well, because we think this will benefit both Twitter and also the Zookeeper open source community, and it will bring us bring our internal forks more close to upstream version. And also, some of the patches might be useful to other, to the open source community and other Zookeeper users as well. So you can expect us to start to simply see some patches from us in the next probably few weeks. That's optimistically speaking, because we are a really small team, and there's lots of work to do. The next thing is we want to definitely increase the observability or visibility in Facebook's term, because I feel we still lack some sort of insights into the system at certain levels. And to really understand the system, we need to really get a more fine-grained understanding of the systems at different level. And the next two items are availability and scalability. So availability is more about, Zookeeper should narrow it down, because of the client traffic or because of the misuse. And unfortunately, we didn't do a very good job. As I mentioned, we previously tried to add rate limiting, but that does not work well. So I'm pretty interested to see, what's the option here. And also, that's next thing I'm trying to investigate, try to basically adding to Zookeeper here, at least for Twitter, because I think the rate limiting is really the important piece that should be available in Zookeeper. And the scalability is more about, it's not just about let's scale Zookeeper to next level. Let's it serve, for example, from millions of watchers to billions of watchers or something like that. So think another way. The scalability can also be think as let's have fewer Zookeeper servers that can serve the same traffic, for example. So previously, we have, for example, we have 10 observers that can serve workloads for certain customers. And how about we reduce it by half? We only have 5 observers. So this is another dimension of the scalability that would be interesting to investigate a little bit. So, and of course, multi-tenancy is, I guess, it's always on everyone's roadmap. And for us, I think it would be interesting because if we really support multi-tenancy, then it's possible for us to, combine some of our not so important Zookeeper clusters into a single cluster, which will greatly reduce the operational overheads of operating the Zookeeper cluster. And there are also some other things we are interested to look at. In particular, we are also very interested to, help Facebook folks to review your patches and also, testing your patches in our production environment. And I think for infrastructure software like Zookeeper, it's probably no better, no better testing environment other than other than testing it on production, like at Facebook or at Twitter, for example, which has pretty massive scale or massive workload. that can review many problems. Okay, so that's about it. Thank you very much.
Thank you. So back to me again. So we're done with the presentations. I know everyone is here to eat and mingle, but I want to open questions. If anyone has any question about any of the stuff we talked about, I would love to hear. Come on. You must have something in mind. Are you hiring? I'm always hiring. That's not a question. That's always true for Facebook. So did I answer the questions that was on the community kind of email list about what's Facebook involvement in the Zookeeper? Are we still invested or not? Does everyone have a good picture of how invested we are? There was a big discussion on, oh, what's the deal with LAD now? Are we clear on that? Yes? You don't have questions for me? Patrick, you don't have any questions for me? We're good? So thank you all for coming. One more slide for me. Yes. Yes. Yes, we need your feedback. So I would love for each one who attended to actually, this should be very quick. Just tell us what you think about the event. What would you like to see next time? Hopefully, I'm hoping to repeat at much faster pace, the meetup, other than last time it was almost 2 years ago. So I would love to do this so every 6 months if possible. So expect to hear us from us back soon. So give us the feedback so the next meetup can be easier. Tell us how was your commute to this nice, awesome building. I'm sure you guys have feedback about that. So thank you for coming. We have swag. So pick up your swag. We have some nice stickers. Then we have food outside, and we have drinks. And let's chat about the food for thought that we talked about. How are we going to release? What's your thought on Java? What else is in your mind? What features did we miss? OK? Thank you.